everyone, and we are into the second mind map for the chapters kinematics. It actually includes kinematics as well as you can see vectors as well. So what we'll do is probably discuss the vectors part first, and then we will move on to the kinematics part. Okay. Now, first of all, what are vectors? I think, yes. Vectors are quantities or physical quantities which has magnitude as well as direction. If it has no magnitude, then, if it has no direction, then it will be simply called a scalar quantity, right? Now, this much you already know probably. There are different types of vectors which we can define, such as a zero vector. What is a zero vector? As I told you, magnitude and direction. If the magnitude of a vector is zero, then does the direction has any significance? No, of course not. If it is a zero vector, it nobody even cares in which direction it is pointing. Actually, it is meaningless in which direction it is pointing. So that type of vector is called what was that? Zero vector. Where is it? Yes, zero vector. So this part is okay, and maybe equal vectors we can discuss now. Let's say there are two vectors which has vector 1 and vector 2, which has a magnitude 1 and magnitude 2. Sorry, direction 1, magnitude 2 and direction 2. These are two vectors. This will be called equal only if both magnitudes are the same and direction is also the same. Alright. Of course, the equality is not a actual thing in directions. We just have to say that it is in the same direction. So those type of vectors having same magnitude and same direction will be called equal vectors. Equal vectors. What about negative of a vector? Let's say there is this vector and this vector. If it is the same length, then they are the equal vectors, right? Equal vectors. What if this is a vector and exact opposite direction and the same length? If this is 2, this is also 2, then a and b are called negative of vector. Negative of a is equal to b. In the same manner, negative of b is equal to a. These are called negative of vectors. These are not negative vectors as such. These are just negative of a particular vector. That is another vector which having the same different direction or opposite direction but having the same magnitude. These are called negative of a vector. Now, co-initial vector actually, if you know about the graphical representation of a vector, there is this straight line. It has a tail, it has a head. Now, if there are two vectors having coinciding tails, if they have coinciding tails, no matter in which direction they are having their heads, they will be still be called co-initial vectors. Co-initial means starting from the same position. Now, I think this is the part of kinematics which we will take later in this session. But continuing with the vectors, there is one very important part of vectors which is called addition of vectors. Addition of vectors. There are two different rules for addition. One is called parallelogram rule or parallelogram law, and the other is called triangle law. Now, coming back to the graphical representation of vectors, let's say there is this vector A and there is this vector B. All right. Or maybe we can take the other vector somewhere else so that it's a generalized maybe example. There is this vector B. There are two different vectors lying in different places, and what you have to do is produce a new vector which is nothing but summation of these two vectors. Then what you will have to do is, for example, what if I make another vector which is exactly the same length and pointing in the same direction? Can I say that this d vector is actually equal to b vector? Of course I can say. Or I can even go on to the saying that this is actually b vector, nothing else. This is actually b vector. Nobody can say it is wrong. What that point means is, you can actually drag any vector into any other position, make without changing the direction or the magnitude of the vector, then the vector will remain the same even if you have dragged it to somewhat a different direction. For example, this is a vector. If I do this and the length is the same, then again the vector is the same. It does not matter, or it does not change with the dragging. So what we can do is place the tails with each other. That is one of the prerequisites for parallelogram law. To apply the parallelogram law of addition, what you have to do is place the tail of one of the vectors to the tail of another vector. We can bring b here such that it looks something like this. This is b vector. All right. If this is clear, let's move to the next part of parallelogram rule. The next part of parallelogram rule says is, now you have two sides. What you have to imagine is, or what you have to draw is a parallelogram which has these two sides, this side and this side. So what you do is make parallel lines and make them touch each other. The point where they touch, from the initial vector or from the initial tail, what you do is draw a new vector which is actually the diagonal of the parallelogram, starting from the tail and ending at the other side of the parallelogram. This new vector, what we have here is c vector. It is nothing but the addition of these two vectors. So this is the parallelogram law of addition, vector addition. The second rule for addition of vectors is triangle law. What this law says is, let's say we have two vectors, a vector and maybe b vector. If you want to add them from this law, be very sure that you do not have to make the tails touch as we did in parallelogram law. What you have to do is, from the head of one, you have to attach the tail of the second. You can do it in either way, the tail of b with the head of a, or head of a with tail of b. Now, what I am doing here is, I can of course move the vector in any direction I please, just keeping the direction same, the pointing direction same, and I can move it parallelly anywhere. So what I will do is, I can write the a vector here. Now it satisfies the condition for triangle law that the head of one side is actually touching the tail of another. What you have to do here is, see, this is not a free end of these vectors. This is a free end and this is a free end. So what you have to do is, from the free tail to the free head, you have to make another vector, or I can choose another color for that. From the free end to the free head, you have to make another vector which is nothing but c vector, and that will be the addition of these two vectors, a vector plus b vector. All right. So I think that is okay. Just a second. Yes. So these two laws for addition of vectors, I hope they are clear to you. So this part is done. Now there is this subtraction of vectors that we'll be dealing now. Let's say there is this vector a and there is this vector b. If we have to do addition, we will just place the tails together so as to satisfy the parallelogram rule. But in case of subtraction, what you have to do is, let's say if you want to find a new vector which is nothing but a vector minus b vector, what you will have to do is, can I write this in the form of a plus minus b vector? Of course I can do that, because first after simplification minus will come out and it will be again be a vector minus b vector. But what has changed here is, I do not have to do subtraction. I can simply do addition, which I already know how to do it, of two different vectors. Vector A and another vector which is not B. It is actually negative of B. So what I can do is, maybe write A vector here, and in place of B vector, if I have to do addition, I will have to write minus B vector, and this can be minus B vector, right? Since B vector was this one. So in the opposite direction. Again, I have to do addition of these to get the subtraction of A and B, right? From this equation. So what I'll do is, maybe place this one at the tail or make the tails join. What this will look like is something like this. A vector, and this is minus B vector. Now all you have to do is addition of these two vectors, which we can do by the parallelogram rule. Make a parallelogram, and from the tails which are joined together, you make another vector which is actually the diagonal of the parallelogram, and this is nothing but C vector, which is equal to A vector minus B vector, nothing else. So did you get it? How we move, how we use the addition of vector itself to get the subtraction of vectors. All right. So this part is also done. Now, this actually tells me that any vector, let's say there is this vector of 2 units and in this direction. What if I need another vector pointing in the same direction but having 4 units? What I will do is, let's say this was a vector and this is the vector that I need, b vector. What I'll simply do is, b vector is nothing but some constant multiplied by a vector. What should be the constant? 4 and 2, right? So 2 into 2 will give me 4, the magnitude that I want for b vector. So this will be actually equal to 2 into a vector. So if two vectors are actually equal in the pointing in the same direction, you just need a constant to equate them, right? Because direction are the same, only the magnitude is differing. So magnitude can be taken care by a constant. Now this has been discussed. Now any other part of no, sorry, I think we can take relative of vector later, but and velocity as well, maybe later. Let me just check with the first one. I think scalar vector part we have already covered, and we can move on to the kinematics part. All right. Let me just check the time. Yes. So kinematics. First of all, in the kinematics part, what we'll be dealing with is maybe speed. All right. Or maybe distance and displacement first. I can also do this. Yes. Let's say there is this particle A, or a particle which is at a position A, and it starts to move in some random path till point B. Now, what is the net distance covered by this object? If let's say this is a road and you are doing a road journey, what will be the total length of the distance covered? You will find that distance by adding all these small distances, right? All these small distances, this distance plus this distance plus this distance. By adding all of that, what you will get is distance covered. But what is the displacement? Displacement means dis plus placement. Means how much have you been, or what is the measurement of the length from which you have been removed from your original position. This was original position and this is the final position. So this should be the measurement of the quantity from which you are measuring the change in position, right? So this is called displacement. There is a basic difference between distance covered and displacement. This is the total distance covered, and while this is the shortest distance between initial point and the final point. This is a scalar quantity. Why is it a scalar quantity? Because it does not have a direction. When you say that I have covered this much amount of road journey, you do not tell that in this direction I covered this much kilometers and in that direction I covered that much amount of kilometers. But in displacement, it is very vital to know the direction. If you are in this direction, the pointing direction tells you that in what direction have you moved finally, or what is the final position of your of the particle with respect to the initial position. That is called displacement. All right, so I hope we know the basic difference between distance and displacement. This is a vector quantity, of course, because it has some direction associated with it. Now we are done with these things. What we will do from here is define speed. How do we define speed? Speed is distance covered by time taken. This is the basic definition of speed. But I think we need to, at this level, be very clear at what or which particular type of speed are we talking about. Let's say a body starts from here and reaches here in time t, from 0 to time t, and this is all the distances it covers, right? So if we talk about an average speed, or the average rate with which it is covering distances, that is called average speed, which is equal to total distance covered divided by total time taken. Okay, so this is, yes, so yes, what I was talking about, total distance covered by total time taken. Just a second, I'll just scroll it up. Yes. And for finding total distance covered, do I need to add the small distances over each of the straight lines so that I know the exact total distance which has been covered by the body? So this is nothing but all those small distances or small straight lines until some final, and also the time taken for this one, time taken for this one, time taken for this small journey, small journeys. If I add them up, I'll get the total time that the body has used. T3 goes to Tn. So this is the average speed, which is, I think, the same as this equation. So I hope you get it from where we got the equation. Now, we also write it in other form. If we talk about this particular distance s1 and t1, can I write the equation for speed for this small part? Of course I can. Speed 1 for this small distance could be written as s1 t1. It means s1 can also be written as v1 t1, which is the speed multiplied by time. In the same fashion, can I replace s1 s2 s3 in the same fashion? So that will be v1 t1 plus v2 t2 plus v3 t3 until all those additions and t1 plus t2 plus t3, because I have not changed the denominator, which is actually equal the same as this equation. So in either way you can find the, or actually these two equations are not very different from each other. It's just the expansion of the distances in the second equation. All right. So if that is covered, then we can move on to the instantaneous velocity. All right. Instantaneous velocity. What was the average velocity first of all? Or we have not talked about velocity, right? Let's just talk a little bit about velocity as well. Velocity. In the same manner as we defined speed, we can also define velocity, which is equal to displacement divided by time, or change in position vector divided by the time taken. Right? Now, the same, if you want to find the change in position vector, you can just, these are scalar quantities s1, s2, s3, but you can take the vector quantities which are position vectors. In case of them, r1 vector plus r2 vector plus r3 vector divided by t1 plus t2 plus t3, like that. And I hope you get it, that it will also be equal to v1 t1 plus v2 t2 and added like that, divided by t1 plus t2 plus t3, in the same manner as we did for the speed. But something is different here. We can also find instantaneous velocity. How can you find instantaneous velocity, or what is instantaneous velocity to be precise? Instantaneous velocity means, let's say the body is here and moving in this direction. At this instant or a very small fraction of time, what is the velocity this object has? Because the average velocity that we talked about initially was nothing but the average of all the velocities over the whole journey. But I'm not talking about the whole journey in this case. I'm talking about only a small segment of the journey, very small segment, and I'm actually talking about the velocity with which the body is moving at that particular moment. That is defined as instantaneous velocity. This can be defined as, let's say, the object here and the object, the final initial position is this one and final position is this one. This is the delta r, or displacement vector, and the time taken is delta t. This must be the average velocity, right? Average velocity. But what if I reduce this gap to smaller and smaller fragments, or smaller and smaller limit, so that the individual thickness or individual times limit that you are given for the measurement is very small? Then it will actually tend to limit delta t tends to 0 delta r by delta t. This will be instantaneous velocity, v instantaneous, right? And this can be written as, if you have learned it about in the mathematics, This can be straightaway written as dr by dt, differentiation of position vector with respect to time. So I hope you are clear with this. I think it is in this one. Yes, this one. All right. Now, average velocity we have already covered. What other things we have already covered? I think velocity. We will take this up in the later part of the session so that it is very clear until that point. What we will be doing now is maybe let me just check which other things are left. Yes, if the velocity, yes, we can take up uniform and non-uniform motion. Uniform and non-uniform motion. And what is that? Let's say a body here is moving at 10 meter per second. Velocity is equal to 10 meter per second in this direction. In this direction. What if this body continues to move at 10 meter per second for time infinity, continuously, with no stoppage? Then that type of motion will be called a very homogeneous motion, or to be very technical, it is called uniform motion. Uniform means very homogeneous, means no difference in the individual velocities at any point of time. At any point of time, if you take the velocity, it will always be the same 10 meter per second. For example, in this case, there can be other velocities as well. So that type of motion is called uniform motion. And what about non-uniform motion? Exactly opposite of this. When the velocity varies, changes, there can be two different type of changes. Maybe if this is at 10 meter per second, after certain time or after maybe 1 second, the object may be moving at 9 meter per second. After 1 second more, maybe it is moving at 8 meter per second. So it is definitely having some change in the velocity. So that will definitely be non-uniform motion. But there can another type of motion which may look to be uniform, but it is not. For example, this is 10 meter per second initial velocity. After after 1 second, it has a velocity of 10 meter per second, but in a different direction. After certain time, maybe it has a velocity of 10 meter per second, but in a different direction. Of course, the magnitude remains the same, but even if the direction is changing, the velocity itself will change, because velocity is a vector quantity. It is defined both in terms of, or both the magnitude and the direction are important for defining the velocity, because it is a vector quantity. In this case, there should also be, this is also an example of non-uniform motion. It is not a uniform motion, but a non-uniform one. Okay. Now, if that is clear, uh, for uniform motion, I don't think there is any need for defining any other parameter. But in non-uniform motion, what I also need to know is with what rate is the velocity changing? Is the velocity changing something like it was 10 meter per second, and then after 1 second it becomes 9 meter per second, after 1 second it becomes 8 meter per second, but in another scenario 10 meter per second and it gets to 5 meter per second after 1 second, and after another second maybe it is getting to 0 meter per second or any other velocity. In these two, of course the velocity is decreasing, but the rate of change of velocity, or with what pace is the velocity changing, is different. So that is why we define a term called acceleration. Acceleration is defined as the change in velocity in a given amount of time. The change in velocity in a given amount of time. This is called maybe average acceleration. Acceleration. All right. It means change in velocity means final velocity minus initial velocity divided by the total time taken. Now, in the same manner, can I define instantaneous acceleration? Of course, we can, using the same logic that delta t tends to 0, right? So, average, sorry, instantaneous acceleration is nothing but limit delta t tends to 0 and delta v by delta t. This can also be written as dv by dt, differentiation of velocity vector with respect to time. This is the part we need to understand here. I think, yes, uniform motion, non-uniform motion already covered, and instantaneous acceleration also covered. I also gave you average acceleration, which can be of some use in some cases, and we already did this one. Now, yes, average acceleration as well. So, what we are left with here is a relative velocity. What other things do we need to cover? And these are the parts of projectile motion. This is also relative velocity. Okay, let's come to relative velocity now. Just a second. Yes, relative velocity. What do you mean by relative velocity? Before this, we were only talking about absolute velocity, right? Means velocity which the object actually has with respect to the earth. But what if you have these two cars? You are in this car and your friend is in this car. This one is moving at 5 meters per second and this one is also moving at 5 meters per second. You are A and this is your friend B. At this point, you both have the same velocity in the same direction. So when you look at your friend in the car next to you, do you see the friend moving with respect to you? Do you see him moving with respect to you? Of course not. If you have the same velocity, then you probably, if you look only at your friend, then it will seem that he's at rest. And if let's say you have another friend in another car which is ahead of you and moving at 10 meters per second, say a friend C here, C, what will you see? What will you see? What should be the velocity of C? Should it be 10 meters per second? Of course not, because you're already moving with some velocity. So you will probably feel that the car next to me is moving somewhat slower as compared to 10 meters per second. Why is that? Because you always see the person C with respect to your own reference, your own velocity. So that means is velocity that person B has, let's say I'm calling this B, with respect to the observer, which is A. This is defined as velocity of B, this one, minus velocity of A. This is the definition of relative velocity, and I will write this is in written format so that it is very clear to you, because people have confusion over it. This is velocity of B with respect to A. It means velocity of B if the observer is A. Alright. So if the observer is also moving, then you have to take care of the relative velocity. Alright. So if this is clear, the relative velocity, I'll give you two different examples. Let's say there's this example in which you are moving with 5 meters per second and your friend is moving with 10 meters per second. But let's say you're moving with 5 meters per second in this case as well, but your friend is moving with 10 meters per second towards you. What should be the magnitude of relative velocity in each of the cases? Should it be same? What do you think? Of course not, because these are all vector quantities and you will have to take a reference. Reference means in which direction are you going to take the numbers as positive and in which directions are you going to take the numbers as negative. For this case, what you'll have here is uh, velocity of B and A and B. Velocity of B with respect to A will be velocity of B, which is 10 meters per second, and I'm assuming this direction to be positive. I'm just assuming this direction to be positive, which in turn gives me this direction as negative, minus what is the velocity of A? Again 5 meters per second in the positive direction, so 5 meters per second. So 5 meters per second. And this gives me 5 meters per second. And if I don't have anything, this is already a positive number, which means it has a relative velocity in this direction, that direction. But what if in this case I calculate the relative velocity? What happens in that case? What happens is velocity of B. What is the velocity of B? 10 meters per second in leftwards direction, negative direction. So I'll write this as 10 minus 10 meters per second minus what's the velocity of A? 5 meters per second in the positive direction. So 5 meters per second. This comes up to be minus 15 meters per second. It means this direction and minus 15 meters per second. The object will seem to be faster than it actually is. Right? So what this basically means is if the direction of both of them is the same, the relative velocity will be smaller with respect to individual velocities. But if they are approaching each other, then the relative velocity will actually be the sum of each other, not the difference. All right. So if that is clear to you, I think yes. Relative velocity, where is it? Where is it? Where is it? Maybe it must have been in written form. Yes, this is the thing I just explained. This is the relative velocity, and in the opposite direction it will be added, and in the same direction you will take the difference. This is the relative velocity. And uh, do we have another part which discusses relative velocity? Maybe later. This is actually the same thing which we discussed, but maybe used later. No problem. What we are going to discuss next is in this part. I think this has already been covered, and these two will be covered at the end of this session. Maybe we can take up this part, right? Position vector and displacement vector. I think I've already dealt with it, but still, I'll just give you a gist of it. If this is the point, let's say x1, y1, then the point with respect to some particular fixed point will give me a position of this point, right? So by convention we use this as the 0 point as the reference. So what the position vector for this case will be actually equal to, what is this? This is y2 and this is, sorry, y1 and this is x1. And in this direction you have I cap and in this direction you have j cap. So you can write it as x1 I cap plus y1 j cap, right? So this is the position vector. Position vector. What if what if it happens that maybe you're moving from this point to this point, which is x2, y2. This is r1. And for the position vector of this one, what you will have is x2 I cap in the same manner plus y2 j cap. Now, from the triangle rule, or the the definition of displacement says it is the difference in position vectors. Final position vector minus initial position vector. So displacement is actually equal to final position vector minus initial position vector, which will be this one. Even if you go by the triangle rule of addition and subtraction, you will get the same thing, which I'm going to write right now. Write it right now. R2 vector, what is that? X2 I cap plus Y2 j cap minus X1 I cap plus Y1 j cap. This can be written in format of X2 minus X1 I cap plus Y2 minus Y1 j cap. This is the change in position of X, and this is the change in position of Y. This is the displacement vector. All right. I think it must be clear. See, yes, this is the position vector and displacement vector that I just discussed. So after that, the relative velocity, I think, has already been covered. We need to get into it. I think we can discuss this one. Just a second. Yes. Now, let's say this is the velocity vector. Right. This is the velocity vector. And what you can do is, maybe you can draw quadrants, and you can break the vector into two different vectors so as to write it in format of I cap and j cap. If this is theta, can we write it as this is v cos theta and this is v sin theta? So v vector should be equal to v, this is v1 equals, and this is v2. v1 I cap plus v2 j cap, right? And what is v1? v cos theta I cap plus v sin theta j cap. We can even write this as vx, because this is the component of velocity in the x direction and component of velocity in the y direction, j cap. This can also be the another format in which you can write the velocity vector. I think yes, this is this one. And since they are perpendicular to each other, see, this is in the I cap direction, right? And this is in the j cap direction. If you have to add two vectors which are perpendicular to each other, what you basically end up with is a square plus b square, vx square plus vy square. As simple as that, right? It will actually come out to be the same, because vx is nothing but v cos theta. So v cos theta whole squared plus v sin theta whole squared, which is actually equal to v square taken common and cos square theta plus sin square theta. And from the basic trigonometry, you must be knowing that cos square theta plus sin square theta for any given theta is equal to always 1. So under root v square, which is nothing but v. What you started with is what you end up with. So this tells us that what we assumed in this case was actually true. This one. And in the same manner, since velocity and acceleration are the vector quantities, we can extend whatever we did with the velocity to the acceleration as well. See, this is almost the similar equation that we have written, and the second equation is also very similar to the second equation. it's just the same thing. From extended from velocity to the acceleration, it is just the vector part which is being discussed, which is not different from velocity and acceleration. Both are vector quantities. All right. So I think we have already discussed this one and this one as well. Now, let's come to uniform circular motion. Just a second. Yes. Uniform circular motion. Let's say this is the pebble, or this is a pebble actually, and it has been tied, or it has been held in your hand here. This is a hand and this is the pebble, and you are whirling the pebble circularly so that it gets into a circular trajectory. Sorry for the bad, or maybe I can draw it again. Yes, circular trajectory. Now, this the speed of this object can remain the same, right? It is a constant speed, 10 meter per second, moving at 10 meter per second, moving at 10 meter per second. Such type of circular motions are called uniform circular motions. But from uniform motion, you must be having the idea that velocity should be same. Does it mean that in uniform circular motion also the velocity should be always the same? Actually, no. Because even if it has the same speed, the velocity is always tangential in circular motion. So, do you see? Even if the speed is same, the direction of the velocity is changing. And if the direction of any vector quantity is changing, the quantity itself is changing. It is not constant. It is not a uniform motion. So, for changing velocities, of course, the velocity is changing. For changing velocity, there must always be a force, or there must always be an acceleration behind it, right? So, the acceleration is actually towards the center. What you do is, by if you have already ever whirled a pebble in circular motion, you must feel that you're always trying to pull the object towards you, but it is moving circularly. So by pulling towards you, what this actually is called centripetal acceleration, which is equal to v square by r. Whatever the speed is, divided by radius of the circular trajectory. I'm going to give you another term here is angular velocity. How do we define velocity? Velocity is defined as uh, displacement in the, or speed. How do we define speed? Length covered per unit time. But the way we define angular velocity is angles covered per unit time. For example, it was here, and after some point it covered angle theta in 1 second. So angular velocity will be equal to theta radians by 1 second. I hope you are getting it. From the distance, we are just talking in terms of angle. So, and since you know that for small distances, for small parts, it is equal to r theta or r d theta, we can write it as v square is nothing but, um, and what is exactly v? V is actually equal to dr divided by dt, right? And if you do 1 by theta, or 1 by r into r, what you have here is dr by r, or r, is equal to actually d theta from here, d theta divided by dt, and this is r. So did you get it? We can replace, since this is actually equal to omega, v is equal to omega r. We came to here. We can replace v is equal to omega r So omega r whole squared divided by r. So this will be actually equal to omega r, sorry, omega square r. This is the centripetal acceleration, and this is also the centripetal acceleration. This is what you need to remember from the whole explanation. All right. So from here, I think this uniform circular motion has been dealt with. The only part which is left here is a few equations of motion which will be used very extensively. I I hope you do a lot of practice on these, because these are the most common numericals from this chapter. The first equation of motion, equations of motion. The first equation is actually v is equal to u plus at. What is v here? Final velocity. U is initial velocity. A is acceleration, and t is time. Now, t is a scalar quantity, except that all of them are vector quantities. So you always have to take care of the direction as well. If you have taken the sign convention as this is a positive direction, then whatever velocity which is in this direction, you will have to plug the, let's say this is 10 meter per second in this direction. Then you will plug 10 here in this one. But let's say the acceleration is minus 1 meter per second square. So what you will do is in A, what you'll plug is minus 1 actually, not the 1. So you will always have to take care in which direction it is pointing. Based on that, you put the sign conventions for these equations. These are not just the magnitude equations. These also consider directions. The second equation is S is equal to ut plus half a t square. S is the displacement, which is of course vector quantity. U, as I told you, vector quantity. A is a vector quantity, and t is just the scalar quantity. So in the same manner, you will have to apply displacements as a negative or positive depending on the sign convention that you have chosen, as well as the speeds and the velocity and the acceleration. The third equation is actually v square minus u square is equal to 2as. In this part, since it is a squared, it doesn't matter if it is negative or positive. The square will always give you the positive numbers. So only thing which needs to be taken care is the acceleration and the displacement in this case, so that you do not get confused between the directions. If you make calculation, or if you make a simple mistake in the sign convention, it will end up to a major catastrophic calculation mistake. So please have a lot of practice in this one. This one I think has been dealt with. Last equation is not that really important to remember. You can just use the first three to solve any problem. I think most of them are very easily solved by this. The last part of this session is projectile motion. So I'll just give you, or maybe I could explain it here itself, so that you don't have to go anywhere else. I'll just erase this part. Yes. So if this is the ground, and with a particular velocity you have thrown an object, it should perform a parabolic path, and it should fall down on the ground, right? There are three things here. First, maybe the range. What do we call range? The horizontal difference in the positions of the pebble from the initial position and the final position. That is called range. The second thing, maximum height achieved. Height achieved. That is this point from the ground. This is the maximum height achieved. And the third part is maybe time of flight. Time of flight. What does it mean is, from the moment it was in air to the moment it it is almost striking the ground, what is the total net time taken? What you will do here is, I'll just give you a very basic thing. What you'll do here is, I will choose another color here. Yes, you will divide this particular velocity into its horizontal component and vertical component. Sorry, vertical component based on a theta. This will be v cos theta, and this will be v sin theta, and all the three equations of motion that I had explained earlier will be applied only on the v sin theta. Why? Because acceleration due to gravity always works vertically, not horizontally. So acceleration due to gravity will always work only on the v sin theta. Everything will vary uh, depending on v sin theta, and v cos theta will almost act as if it is a uniform motion, and whatever time it is allowed in the air, it can run up till that time with a uniform velocity. When you do that, solve those three parts, you will get the total time taken is t. Where will you get that? Since you have the upper velocity v sin theta, you can get the time taken to get to a point where the vertical velocity will be equal to 0. Vertical velocity will be equal to 0, and the initial velocity you have already have. So the time from this point to this point you will get, and that is equal to the time to the same, it is equal to the time it will get to reach the ground. So that will be the total time taken. Whatever you will calculate here, it will be the same here, and the total time taken will be 2t. The maximum height achieved, you can easily get it from the third equation of motion, because you already have the initial velocity and the final velocity and the acceleration due to gravity. So you will get the displacement, this one. And the range, it is very easy, because you have the horizontal component of the velocity, which is an independent motion, which is a uniform motion in the horizontal direction. So you just need to multiply by the time of flight, the amount of time it was in the air, the horizontal velocity it could act on it. So that multiplied by that will give you the range, which is this one. The equation for the motion is not really that important, but these three things are. And most importantly, the three equation of motion that I discussed previously, if you have that very well uh, revised and very well practiced, you will not miss any problem in this chapter. So that is all from my side, and I think I hope this mind map helps you, and thank you.